So considering this closed loop response of the system, so let's say that the original uncompensated system, this was its magnitude. Okay, so this is the magnitude response of the system, and this is the phase response of the system. Okay, so we know that the critical points are, this one is minus 180 degrees with 0 dB in the gain. So this is the point that we want to avoid, as we mentioned when we talked about the gain margin and the phase margin. So we always want to avoid these. So the gain margin becomes how much gain you can apply to the system before it becomes unstable. So you push this above until it reaches this point. So when the gain reaches this point and the phase is minus 180, the system is unstable. The same thing happens if you add delay to the system. So if you bring this phase plot downwards until it reaches minus 180 and it coincides with this gain crossover frequency. Okay, so this is the gain crossover frequency. Okay, so when this happens, then we tend to have this instability. So we can see that the uncompensated system has a phase margin and a gain margin like those indicated in this figure. So what if we want to add a compensator now? So let's say that we will consider this phase lead compensator. Okay, we already examined how the phase response looks like and how can we make use of this. So if we were able to put the zero and the pole such that we are able to somehow increase the phase in this critical part. So because we know that the Bode plots are just added together, right? So if we are able to bring this part over here and put it such that it's added on top of this phase response, such that it brings this phase above a bit, what will happen to the phase margin? So the phase margin will increase. So instead of this, it becomes like this. But we have to notice that in addition to the increase of the phase, also the phase lead compensator is also affecting the gain. So it will shift this magnitude plot a little bit. So the gain crossover frequency will be shifted, and this actually means that eventually we will have the new phase margin, which will be something like this. So this becomes our new phase margin. Okay, so we have clearly increased the phase margin of the system. So when can we use such a compensator? Okay, we can use it if, for example, we have a system in which we want to the system has very low phase margin and we want to increase that phase margin, but at the same time the system has quite sufficient gain margin. So we add a phase lead compensator in order to give the system more tolerance for delay. Okay, so this is one of the main objectives of the phase lead compensator, and this is how you can examine the control system design using the Bode plots. So the good thing is, as we said, that using this Bode plot with the magnitude and phase response, we can easily just add the compensator response on top of the actual response. So this one was the G of omega, and then we add on top of it, so this becomes the G of omega multiplied by GC of omega, which is in the log domain, it's actually becomes addition because we take the log of this and the log of that, so it becomes addition. And the same thing happens for the phase. The phase automatically is added. Okay, so you can see that the phase margin can be enhanced using this method, and this is at least one way of designing a phase lead compensator and one clear control design problem. So you can have a controller in which you have in the specifications, okay, you want the phase margin to be greater than a certain number, for example, let's say 40 degrees or 50 degrees or 80 degrees, okay, and you are required to design a compensator, for example, a phase lead compensator, such that this requirement is satisfied. Okay, on the other hand, okay, we notice that the phase lead compensator is sacrificing the gain margin a little bit, not too much, but the gain margin has been reduced a bit. So you need to be careful about that. And the other thing is that also it increases the system bandwidth. Increasing the bandwidth of the system. So yeah, we can see that here we have wider bandwidth with the compensator. So increasing the bandwidth is both a good thing and a bad thing, like anything in design in general. So when we have a higher bandwidth, okay, so this high bandwidth implies that, okay, the system is faster. Okay, it can respond in a faster way. So when we have a step response, for example, we would expect that our controller would be relatively fast, which is good. It would settle quite fast. But on the other hand, increasing the bandwidth also makes the system more problematic in the presence of noise, because the system, when it's fast, it can respond quite fast to any input, but it also responds to noise quite much. So we need to be careful about this. So these are all these kind of different trade-offs that we need to be careful about when designing our control systems. Okay.